Okay, so welcome back. We're talking about extending our trigonometry to oblique triangles, triangles that do not have a right angle. So, let me point out something. We've got SOHCAHTOA, which you are very familiar with, in our right triangle trig. We've got an angle theta, and the opposite side to that angle, the adjacent side to the angle, the hypotenuse, and you're used to the definitions of sine, cosine, and tangent in terms of those sides in a right triangle. And you're used to the sides of the triangle being a positive distance. And that's all good, and we can imagine this triangle rotating so that it looks like this. And theta would be here. We can imagine reflecting that or flipping it around, and then we'd have something like this. Right angles. Okay, now those triangles, they can be anywhere, right? They could be the corner of a room, they could be the corner of a box, they could be wherever, and you could put them all over the page. You can turn them around, rotate them, shift them to different locations, and that's all good. But now, to extend our trigonometry, we're going to take that triangle and locate it at the origin. We're going to put our angle, theta, so that that vertex is at the origin, and we're going to then graph it so that all of the points, all of the vertices, can be identified by their coordinates in the Cartesian coordinate system. So, we can also scale the triangle, right? We can get closer or further from it so that it, or we could shrink it, or we could dilate it larger or smaller. So we're going to do that. We're going to dilate it. We're going to locate it here and say that we've got this triangle right here. Alright, so let's say that's our triangle, and we have now located this angle theta so that the vertex is at the origin, and so we'll label this the origin A, B, C. A right angle is at C. Okay? So, now angle theta is located so that it is in standard position, which means that its initial side is the x-axis, starting at the origin, and is the x goes in the x-axis direction, and then the terminal ray of that angle, ray AB, has rotated counterclockwise, so it's a positive angle. Counterclockwise rotation, by convention, is positive. It starts at 0 degrees or 0 radians, and we go positive, 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 all the way around is 360 degrees, as you know, or is 2 pi radians, as you also know. And so, this point B is 4, 3. So, we've located our triangle there, and sine of theta, as you know, is this side, this opposite side, divided by the hypotenuse. Now, one thing you are also aware of is that if I were to make a line that was perpendicular here, I could put a perpendicular line anywhere, and that angle wouldn't change. And so this smaller triangle is similar to our big triangle. And so we could go all the way down here to where we have circle, this is called. It's called a unit circle because it has a radius of 1. And if we were to make our little bitty triangle right there so that the hypotenuse was 1, the hypotenuse would hit that unit circle, and so that would mean the hypotenuse would have to be 1 because that's the radius of the circle. Then we have this new situation where we can talk about the sine and the cosine and the tangent of that angle in terms of a hypotenuse length of 1. Now that does an interesting thing with our SOHCAHTOA. It makes the hypotenuse change to 1. And our fraction now is very interesting because the sine of theta is just equal to the length of the opposite side. Alright, so now I'm going to change our graph because this is too small for you to see, so let me erase this a moment. And we will say that this point right over here, this point, is 1, 0. Okay? So now, this distance from the axis out to here, this distance is 1 unit. Okay? 1 unit. So now, this is our unit circle, alright? And we'll look at this situation. We're no longer looking at the same triangle, but we are looking at a similar triangle to the one we were using to define sine and cosine and tangent. So we still have this angle, theta, and we know that because this distance, the radius of our unit circle is 1, that this hypotenuse also is 1 unit. The hypotenuse is 1 unit. And so the sine of theta is equal to the opposite side length, whatever that is. It's not 4/3 anymore. Because this distance is 1. This distance is 1. And so the sine is this vertical distance divided by the hypotenuse. Well, the hypotenuse is 1, so that means the sine of theta is just this vertical distance. Ah, this is interesting because our coordinate xy, that's interesting because y, this distance, we just said is the sine of theta. Okay, that means that we can label that point with xy coordinates, but we can also label that point with the equivalent. We know that sine of theta is our y, and what's our x? What's our x? It's this distance. It's the base of this right triangle. Okay, well, cosine of theta is the adjacent side divided by the hypotenuse. The hypotenuse again is 1, and so the cosine of theta is this distance. Well, that's the distance to x. The x coordinate of that point, that's that distance. So, cosine of theta. Now, any point on this unit circle is going to have coordinates cosine theta, sine theta. So we can give the coordinates with the Cartesian system, x, y, with numbers, but on the unit circle we can give those coordinates of any of those points with trig functions. Cosine of theta for the x coordinate sine of theta for the y coordinate. But let me remind